Hey, welcome to Dr. Pat TV. We are doing the definite integral. I'll also be looking at the fundamental theorem of calculus in a few moments. Don't worry about these technical terms. It's not so bad. All right, so just to kind of review really quickly, remember when we were calculating areas, before we were making little rectangles, we were estimating the area underneath the curve. We were making these geometric shapes, these rectangles, calculating the area of these rectangles, and then adding up all those areas. Okay, so that's what we did before. And then we also know that when the rate graph is above the x-axis, that area is a positive area, adds. And if the rate graph's below the x-axis, it's a negative area. And remember, it's always the area between the graph and the x-axis. So I'm not going below the x-axis when my rate graph's above. And so this negative area there, it's always between the graph and the x-axis. And then also we learned this nice little symbolic here, just basically is our symbolic way of saying the area between the rate graph and the x-axis, going from the left side, that lower limit of a, to the upper limit, the larger of the x values, to b. And so that's what we're playing with. Okay, so here's basically what we have. Just a review of that really quickly, is that symbol there, that definite integral, is that area there. So it's between the rate graph and the horizontal axes, and our left side is a, that's that lower limit there, and our upper value b is the upper limit of the integral sign. Okay, so that's what we're looking for. So we're looking at area between the graph and the x-axis, a and b. All right, so now how do we do it? I'm just going to basically tell you the steps to calculate this. If we're doing algebra or doing the derivatives, the antiderivatives, this is what we do. First step is you take the antiderivative of the formula that we're being given. Then you plug in b, you plug in a, and you take the difference of those results. It's a four-step process. That's all we've got to do. So when I see a symbol like here, the symbol up here, this integral symbol with this a number here in the lower limit and a number here in the upper limit, it's basically two ideas for me. It's a geometric area, and also it's a recipe. It's a recipe of steps for me to do the calculation. All right, so let's do an example. I've got the integral between 1 and 4 of 3x dx. So that's what we're going to do. Now, what does it mean graphically? I've got the graph here of the line y equals 3x. I've got on my x-axis, I marked 1, I marked 4. Basically, what we're looking for is we're looking to calculate that area between the graph and the x-axis. Okay, so between 1 and 4, that's what we're looking at. Okay, so how do we do this? First step, take the antiderivative. The antiderivative of 3x is you raise 1 to the power, and then you divide by that new power. So 3/2 x squared is my antiderivative. And then you're seeing this vertical line. Sometimes you see this in textbooks and in math classes. This vertical line is basically saying, I've done the antiderivative, but it's a reminder for me that I still have to do the calculation. What we have to do is we have to plug in the 4 and then plug in the 1. So we got to plug in that 4, plug in the 1, and then take the difference. So I plug 4 in for the x, I plug in 1 for x, and then we take the difference of those results, and I get something like 22.5. So that's the antiderivative. That's the definite integral. We're getting a definite numerical answer here. And so what did these steps mean graphically for us? So when we do the antiderivative, plug in 4, plug in 1, take the difference, well, how do we get this area? Here's how we get it. So when we take the antiderivative and we plug in 4, we're kind of technically in a roundabout way getting this area between 0 and 4. Okay, a rough estimate. And so that's what we're looking at. And then when we take the antiderivative and plug in 1, we're getting this little green area right here. We're getting this calculation. And so then when we take the difference, that's the whole area here between 0 and 4, take out the 0 to 1 area, and guess what? We're left with the area that we wanted, the area between 1 and 4. And so that's kind of what the calculation, a weird way of looking at the calculation, that's what it represents for us graphically. Okay, let's do another, it's the fundamental theorem of calculus. Here is that fundamental theorem of calculus, basically saying that if we're taking the integral from a to b of f of x dx, f of x is like the derivative. That's the small f. The capital F is the antiderivative. That's basically what we use over and over again, using uppercase, lowercase to indicate which one's the derivative, which one's the antiderivative. And so what we're saying here is take the antiderivative and then plug in b, plug in that upper limit value for the integration, then plug in the a value, that's that lower one there on the integral sign, and then take the difference. It's a four-step process. And so that's what the fundamental theorem of calculus is just basically telling us. It's a nice way for us to calculate and to get the definite integral, to get an answer here. So let's do an example. Going from 0 to 2, and we've got the function 7e to the 5x. So our first step is to take the antiderivative, and that's what I've got here. The antiderivative of exponential is itself, but because we have that 5x, we've learned one of the tricks of the trade is to divide by that 5. So here's our antiderivative. I still have that vertical line right here with the 0 and the 2 to tell me that I still have to plug in 2, plug in 0, take the difference. So I plug in 2 into the antiderivative. I plug in 0. And then I take the difference. And so then that would be the result that we'd get for when we do the definite integral. And so what's happening here is you can type this into your calculator, get a numerical answer. Basically what I did was I factored out a 7/5 because I see that in both terms. And then e to the 5 times 2, that's e to the 10th. That's where that came from. And then 5 times 0 is 0, so e to the 0 is the 1. And so basically factored out the 7/5 and then left the e to the 10, and then that's really e to the 0, which is 1. And so that's an example of doing the definite integral, which we're using the fundamental theorem of calculus, this relationship that says take the antiderivative, plug in your values, take the difference. Thanks. I hope that helps.